want to preview a few derivatives that will be coming up soon. The trigonometric functions, at least in the OpenStax textbook, aren't really addressed until a later section, I think 3.5. And the other function I want to talk about in this video, the exponential function e to the power x, that actually isn't even discussed until section 3.9. But I want to introduce those functions and their derivatives a little bit early. So I'm going to do it in this video without much in the way of proof. I'm going to hold off on the discussion of why exactly it is or how we can prove that the derivatives are what they are. Rather, I just want to introduce them from a more intuitive perspective, or in the case of e to the x, I'm just going to tell you what it is and you can kind of take it on faith. But for now. But with sine and cosine in particular, we can study them from a graphical perspective and figure out what we think the derivatives are and be quite convinced without seeing a formal proof. Let's do that. So let's start with sine. Here's the graph of the sine function. Let's just think about, play the game that we played in a previous video where we're trying to graph the derivative of this function. And let's do a nice orange here. So it's going to be some points like this where we're going to have horizontal tangent lines, right? This point, that sort of thing. So for those points, I'm going to go ahead and plot, blue perhaps, plot the derivative at 0. Okay. Now, looking at this, we see the derivative is going to be positive on this interval here, where sine of x is increasing. Then when sine is going down on this interval, it's going to be negative. It's going to be positive, and it's going to be negative. So alternating back and forth. How positive or how negative? Well, the steepest point, if you look right here, the tangent slope here is about 1. Like if this is 1, you know, we go like up 1 over 1. That's about a slope of 1 on our graph. So, and it is, in fact, it actually does equal exactly 1. So we would graph the derivative right up here. That's as high as it goes. And down here at this point, like this point here, your derivative slope turns out to be -1. So we're down there. And so we're sort of flipping, alternating back and forth like this. And you can start to see exactly what's happening here. You can guess. If I start graphing this derivative, what is it? You can see what it is. Compare that to what's graphed directly beneath it. They're the same. This is the cosine function down here. And you can see that the derivative of the sine function matches exactly the cosine function. So we can write that over here. We could write derivative of this sine function is equal to the cosine function. And that is true, as long as we're dealing with radians. As long as x is in radians. Turns out radians versus degrees is very important in calculus. In calculus, I'll say this now, but I will say it many more times. In calculus, we work in radians almost exclusively. Okay, the derivatives we're going to learn for sine and cosine depend on the inputs being measured in radians. If you measure inputs in degrees, then the derivatives are different. They are different by a constant factor, so not like significantly different, but at least different. So yeah, so just make sure in calculus, almost all the time we'll be working in radians. And if I ever give you a problem that's not in radians, probably the first thing you should do is convert to radians, and then go from there. So yeah, so there's our derivative of sine. That's nice and easy. Let's do the same sort of analysis for cosine. All right, where are zeros? Where are our horizontal tangents? There's one. There's one. There's one. We have, no, that's it. So for this, I'll graph it in red. Put it there, there, there. All right. And now we're going to be, looks like negative on this interval, and then positive, and then negative. right? So let's see. Again, the maximum slope here is -1. So I said maximum, but I meant steepest. I guess it's technically a minimum if it's the biggest negative number. This reaches a maximum of +1, so we can plot that point right there. And again here, we go. And we start to see what this looks like. It looks like this. You know what this is going to be? But you can guess. What is that? Compare it to the sine function above. Not quite the same. Opposite. So if you were thinking, oh, they're just going to be derivatives of each other, not so, not quite. Like almost, but not quite, right? The derivative of the cosine function, when we graph it, compared to the sine function, it's the opposite, like a reflection over the x-axis. In fact, it's the negative sine function. Take the derivative of cosine of x, you get the negative sine function. Okay, so sine and cosine, cosine describes the rate of change in sine. Sine describes the negative rate of change in cosine, or otherwise spoken, the rate of change in cosine is negative sine, the opposite of sine. So, so we're going to take those two derivatives and we'll take them for granted. We'll prove them more analytically later in the semester. More rigorous proofs. The third derivative I want to give you so that we can start using it right away is this one. If you take the derivative of the function e to the power x, the exponential function, you know it well, this one. That one. The derivative of that function is indeed itself. That is a very special property. Not a lot of functions have. In fact, this is pretty much the only function that has that property, up to a constant multiple. Yeah, it's a very special property. So some like shiny stars around it, so you can see how much it shines. Very shiny. It's almost the defining feature of e to the x. It's almost like the thing that makes e what it is. It's like defines e practically. There's lots of ways to define it. You can take this as one of them. Make a function, try to make a function that's its own derivative. And e to the x inevitably is what you will make. So yeah, so we're going to use that along with the derivatives of sine and cosine in the next few videos.